Alright, so this is the Python version of the homework problems. I just wanted to run through them real fast. You've probably already started, um, but let's see what we've got going on here. Um, Let me pause and move over to the right folder. Okay, I should be ready now. So we were looking at problem one, and problem one is just the TGF classification, and so we're going to be doing the wine classification using a linear neural net. Okay, and so let me double check. Are we going to use, I can't remember now if we're using online updates or all at once update. Let's see, problem one, what are we going to do? Linear classifier for the wine data using all at once training with the pseudo inverse. Okay, so that's easy. No need to see that. Well, we'll talk about the RBF. So in my sample code, I'm actually using Woodrow Hoff, but you can ignore that, right? Because Woodrow Hoff is online training. So there is another example where we do batch training. So you may take a look at that. Yeah, in this case, I'm actually using the Woodrow Hoff algorithm. But that's okay. If you want to, you could try using Woodrow Hoff. It's kind of a fun algorithm to try. It's very similar to what we've got here. Yeah, let's give this a try now and see what happens. You know what I didn't do? I meant to do it to see if everything works. Oh, good, everything works. What I meant to do was, okay, we've got the confusion matrix. I meant to get the plots of the T and the G and the F from that you'll see in the MATLAB version, but I didn't get those plots up. But I do have all the classifications here. It's pretty straightforward. So notice here what our training values are. So what are the targets versus what are the values that you put into the confusion matrix? Well, the targets that we're using are the, since we have three classes, we're going to be using the columns of the identity, the 3x3 identity. And so, so for target, or for class 1, we're going to identify that as 1, 0, 0. Class 2 is 0, 1, 0. And class 3 is 0, 0, 1, right? And so I should say on the other side of this, when we do our values here, in fact, let's take a look at these. Let's take a look at T versus Z out. Well, if we look at T, those are our targets, our desired values. And then if we look at Z, that's what comes out of our neural network, right? And so there's some rounding going on here. So you could actually round off the Z if you want. I think I can probably do it this way, can't I? We'll find out. Oh yeah, there we go. And so you see that, of course, it trained perfectly. There's only 6 data points. So this is just a toy problem. But this isn't what we want to feed to the classifier or the confusion matrix. The confusion matrix wants a vector of scalars for the classes. And so to get that, I show you here on line 62 and 63 how to convert the matrix of values to a scalar. So Z out is the conversion, and so this is what we're passing to the confusion matrix 0, 0, 1, 1, 2, 2. And then similarly, we can convert our targets to vectors on line 63, and we also get the scalars 0, 0, 1, 1, 2, 2. So here you can see, that the predicted values are equal to the true values. Good. And then down here at the bottom, we just plotted the error values, epoch error. Good. And so this is how you use the Woodrow Hoff update rule for classification. Okay. So this example is really for this part down here. For the other part, remember how to get the Woodrow Hoff algorithm? So the Woodrow Hoff algorithm is just training Wx plus b, right? And so you can solve Wx plus b directly. So if you don't remember how to do that, just take a look at the notes. because it'll be very similar to the RBF. Actually, if you look at the RBF version of our stuff that we did in the video today, video 1 I think, you'll see us converting an affine map to a linear map in order to solve it. Okay, so I probably rambled on about that example long enough, so let me clear that out, and then we'll clear this out, and we'll clear this out, and we'll take a look at problem 2. So let me get the folder going here, and I'll be back in a second. So problem 2, I look at the Python file, and I see actually 2 Python files now. So I'll pull these out. Oh, so I need to open them over here. So you need to open both the OLS and the YNAP 0. OLS is the module for YNAP, and so let's go ahead and do that. Oops, I forgot to change my folder. Be right back. Okay, so you see the 2 files, ols.py and ynap0.py, so for Python. Good. So what I did, painstakingly I would add, is I went through our MATLAB file and I converted it over to Python. I'll tell you, that was some fun stuff. Well, actually, it was rather enjoyable. It took a little bit more time than I thought, but I understand a few of the idiosyncrasies of Python a little bit better now. Because some of the things, when you're programming in a specific language for long enough, you forget what it was like when you were programming in other languages. So this was a good practice for me. So you see here the orthogonal least squares algorithm. So let me just point out a few things about it. It brings in the data points P and the targets T. EG stands for error goal. I should probably write these down. Well, if I write them down now, they still won't be there, but you can refer back to the video. SP is the spread. So if you don't know what spread to put in, just put in a 1. And MN is maximum number of neurons, And so that way you can stop early if you don't want, if you have 500 data points, and the orthogonal least squares may send you all 500 data points as centers. So if you don't want it to do that, which you don't, then you should say that give the maximum number of neurons. So that's kind of a there's not a hard and set rule for what the maximum number of neurons are. What we want to do is try to get to the error goal, right? So if you get to the error goal using less neurons than that, then the algorithm will stop. But of course we don't know that, and you don't know what your error goal should be. So typically, you would do something like error goal is like 0.1. That's a good starting point. Spread is 1. That's a good starting point. Neurons, maximum number of neurons. If I have 200 points, then maybe I'll say, 100 neurons. I wouldn't want to go too much more than half the data being centers. That's getting too close to memorizing the data. Okay. This other thing, B here, this line, is where we set the spread of the Gaussian function. So this is hard coding the Gaussian as the transfer function. Okay, let's see, we take when you see rad bas here, radial basis, this is going to be the exponential function, and it's being applied to the distance matrix. Now I was transferring code from MATLAB to Python, and so this distance matrix isn't the way I would code it. I basically, if we take a look at what the distance function is down here, it's a wrapper for Python's cdist function. So I just changed some of the matrices around so that they're in the right form for the cdist function rather than MATLAB's dist function. Okay, because MATLAB assumes that don't ask me why. One of the matrices is number of points by dimension, and the other one is dimension by number of points. Well, they're reversed of each other. Anyway, it's a silly thing that they did. so it makes it hard to predict what sizes have to go in. But it all works right now. These are actually all internal to this code, so you shouldn't have to mess with it very much. But I just wanted to say that's why we're not just using cdist directly in the code. So the dist function here is just a wrapper for Python's cdist. So normally you would just use cdist, and that's what we're doing in another piece of code that you'll see. Okay, and then so P here is capital Phi actually, and then PP is P squared, and that's we're taking. You can see here that we're summing the columns through, and then we're transposing that so it's a vector, or so it's a column vector of column norms, which is kind of confusing. And then here, this column, this little d is actually the targets, but it's transposed. And again, we're following along with the dimensions that MATLAB had put together, and so that's why these might look a little funky. But line 27 is the most important one. Line 27 is where we're computing. See, MATLAB says it's the errors associated with the vectors, but those aren't the errors. What we're trying to find is which vectors of P are in the same direction as D. Remember how we talk about that in the homework, and so that's what this actually is kind of mysterious looking here in line 27, but it's actually computing the cosine squared between the columns of P and the columns of D. So that's what's going on there. And so you might take a little bit of time to look at that and see if that's actually true. The next set of lines here, line 30 to line 38, are basically just bookkeeping, where we're adding things to vectors and moving things away from vectors, because we're trying to keep track of which columns we've used and which columns are available, and so we have to do a little bookkeeping with the design matrix. You have to remove columns and add columns. Okay, anyway, that's what's going on here. Good. And then here we are actually computing the error associated with our center. And so this is actually just using one, so that's not going to, I don't think that will get us where we want to be. But basically the loop goes through the exact same computations, so it just goes through and picks out the column that we're going to currently use for our center, and then it's going to compute the error. Let's see. Yeah, and then okay. So yeah, this W is actually left over from our previous iteration, and because we don't pick our new column until here in line 57. So lines 52 through 55 are kind of just setting it up with the old center that we picked before. Okay, and then lines 57 through 66 are computing which column we're going to pick, and then lines 68 through 72 compute the error associated with our new set of centers, and then we check to see if we're done yet in lines 74 and 75, and that's it. And then here we just set up some variables that we return. Okay, very good. And so in MATLAB we would have a little data structure and put like a netparams.c would correspond to, would store C, and netparams.b1 would store b1, and so on. But I thought here it would be better to use a dictionary, and so here you go. In RBF, let's see where, here's where I set up the dictionary. So once RBF OLS is done, right, once it's done with the OLS algorithm, then we formulate the dictionary net params, and then RBF predict will use those net params to predict on a new data set X and give you the new output Y. Good. So you think this will work? I hope so. It took took a long time. So remember to import your OLS. OLS is the thing we built. Okay, so let's see if it runs. Yay! There's our confusion matrix. So everything is here. I think everything is working nicely. So when you go to do your own classification, it should be fairly straightforward. All right. Um, Let me pause. We'll take a quick look at problem 3. Okay, we have problem 3, and we're looking at RBF regression.py. And now the thing is with this file, the other file used the orthogonal least squares to set the centers, and in this file we're going to be using k-means to set the centers. Okay, and secondly, we're going to be using the RBF regression instead of classification, and that's just to give you a sense so you can see how that's used. Okay, and so let's see how this is used. Number one, do I need my OLS file? I don't think so. Nope, we don't import that, so we don't need the OLS module. So everything should be built in. Notice now we're going to be using CDIS directly, I think. We have our k-means algorithm for the cluster centers. And so step 1, get or create the data. In this case, we're just creating kind of a fake data set here using the sign function. And so once I get the data in X and Y, I split it into training and testing sets. And then I perform k-means. So you you get it. Okay, we set up our k-means command here, and then yeah, then we just find the cluster centers. Pretty straightforward. The tricky thing is to remember when you need to do the NP new axis. I found that sometimes that's really important, and sometimes you can leave it off. So when we're doing linear algebra computations, though, I think it's important to put it in there. Good. So once you've found the centers, notice the centers are in matrix C. Then you just go in, and here's the spread command, or spread computation, just like the last time. Now we don't have to use, we don't have to call our own distance function. We can use MapPython's built-in cdist function. So line 44 is the distance matrix. Line 45 is the design matrix, phi. So you're just calling the exponential function on your distance, right? Line 46, we're just taking a note of our columns and rows here. I should have said NRNC, oh well. That's kind of confusing, isn't it? Or AB maybe. Okay, then we remember we have our phi hat and our w hat, and so those are being explicitly constructed here. How do those get constructed? In this case, you're stacking a row of ones at the bottom. So this is the vertical stack. They go on the bottom. And then for w hat, you're adding in oh, actually, we're solving for w hat. We're not constructing w hat. Yeah. So w hat is going to be y train times the pseudo inverse of phi hat. And so this is computing w hat. And this is just a reminder that w hat is wb. Okay, so this is how you solve for your weights and biases. And so step 3 here is training. Step 4 is predicting new data on your parameters. And so this just goes through the simple set of commands that you need in order to output the RBF on new data. So the SPR doesn't change. The D matrix changes because you have to use a different set of data here for your for the second set here. Instead of X-train or X-test, it would be whatever data you want to be predicting on. Once you get your distance matrix, compute phi. Once you get phi hat. And then once you get phi hat, if you already have w hat, then you can figure out what your output is, right? So otherwise we would solve for w hat. And so this line 65 here does all the things we need. Good. And then the last thing is just to show the results. Um, some people were saying, if you have multi-dimensional output, what you can do is plot each coordinate out versus your test out, and the data should lie along the line y equals x. And so that's a good way to test to see if your output is close to what it should be. So if I have like 3-dimensional output and 6-dimensional input, I could plot each of the outputs versus each of the predicted outputs. So I would have 3 graphs. Okay, that's a good way to visualize things because we don't have a confusion matrix anymore. Good. So now that I've talked my way through that, let's see if we can run this sucker. Did I get an error? Oh, reloaded modules. Why did it reload that? We should not have needed that module OLS. I'm not sure why it reloaded it. There's nothing here about it. And I don't have it here. Okay. So it's just some extra stuff, I guess. I didn't remove it. So, good. And so here you see we're getting some beautiful results. Of course we are. I coded it up. Of course we would get beautiful results. What did you expect? Okay, good. So now it's your turn. I've talked enough. Write up your results. Put it in a beautiful format. Good. I'll talk to you later.